Welcome all to this fourth lecture of Principles of Statistics. I have received some feedback from some student, for which I'm very grateful because it allows me to clarify maybe something that I didn't clarify enough. And so his or her question was about the motivation to introduce the likelihood principle. And so, what this student was saying is that it doesn't feel like I have motivated it enough, other than simply by saying, well, this is a continuation of Stats 1B. And I mean, I'm not sure I'm going to give a much better answer than that, just because I presume it's just a very natural idea, this likelihood principle, but maybe let's just recap a bit about it and maybe this will answer the query. Or if not, then feel free to submit a more precise, I guess, idea that you would like to get or understand, or that you want to dwell into detail of it. So I guess, the likelihood principle is a very, very natural one in that, I mean, after all, when you're doing statistics, you have, you're always going to need some data. And data is, of course, something that you cannot anticipate exactly how it is going to be, right? Otherwise, we wouldn't have to have any statistics. So the statistics is really about learning from this sort of randomness, from this, inability to predict. Let's try to find something fundamental about it that then we can use to have some sort of inference, or to make some conclusions with some probability, say, So once you accept, or once you take for granted that there is some randomness in, what you're going to observe, and I don't, I'm not going to go into details as to what randomness really means, and that's a very interesting discussion, but not for this course. But let's call randomness something like the inability to anticipate exactly what is going to happen. And so once you have that, if you want to do mathematical stats, right? So if you want to do something in which, you can do some maths for, then you need to formalize it. Now, if you formalize it, then you have essentially a, probability space and a measurable space, and then a mapping between them. And that really is everything about, everything you need to describe or to formalize a random variable. And so once you have a random variable, as I said in the very first lecture, this is equivalent to having a distribution. Once you fixed the spaces, and so of course that's totally natural, right? So you've got a distribution, and once you have a distribution is really just this sort of underlying fixed quantity that you can understand, so that then you can make probability statements about the data. So the data may be random, but then there is something underlying that is fixed in some sense, and that will be the distribution, right? And so once you accept everything that I've been saying, so if you bought everything in my argument so far, or in my reasoning so far, then what you're left with is this, probability distribution, which may be described as we're doing here through a PMF or PDF or other ways, but at least those two are the ones that we're considering mainly. And once you have this PDF and this PMF, then that has a some sort of intuition as the probability of observing a given observation. And so of course if you then propose a model for this, which is something you have to do if you are thinking of doing statistics, so it's just unavoidable to essentially not assume something, otherwise you wouldn't be able to really reconstruct much about the whole distribution. So you need to to somehow embed it into some space so that then you can say something about it. And once you do that for, I guess, finite dimensions or just any dimension, a natural way of parameterizing this is through some sort of parameter space, as we were saying. And so then you've indexed the family, and you want to think about what is the best element in that family that, or well, the most likely element in that family that will give rise to the observation that you had, right? And so then if you assume independence and so on, then you have, products of these guys. And this is all, by the way, of course, implicitly assuming that we have some sort of frequentist understanding of statistics. Yeah? So we have some, philosophical assumption that the data is generated by a single distribution that actually, is parameterized by this space, and it has just one element that is giving rise to everything. And so once you have that, really, the question is, how do I choose? How do I choose a good function of the data that describes, whatever I want to find? And so then, the likelihood principle is as simple as saying, well, let me look at the parameter from my, family that maximizes the probability of having observed this data. I'm not sure I can give a much better answer than that, because that's just basically the most natural way of, having a frequentist estimator, I feel, given all this reasoning. And let me maybe mention very briefly, just to extend a bit more on this discussion, is that, and I'm jumping ahead a bit, but you could perfectly say, well, but I could come up with other ideas, right? And certainly you could. I mean, all I'm saying is that the likelihood principle is a very natural way of doing it. And there is, you can think of the Bayesian methodology. So I'm jumping ahead a bit, but let me maybe sort of anticipate something about it. And it's that, you can look, as I said in the previous lecture, you can look at the Bayesian methodology, from a Bayesian philosophy or from a Bayesian frequentist, from a frequentist philosophy. And if you look at it from a frequentist philosophy, then it is simply what you're going to do in the Bayesian methodology is to say, well, good. I mean, this likelihood, yeah, okay, that's important, right? Because it's describing all of the probability for the whole space of them. Why would I take only one aspect of that likelihood, right? Which is the maximum in the case of the usual likelihood principle, right? And that's completely fair. I mean, that's a completely fair criticism, and say, well, yeah, let's do something else. So what you do in the Bayesian methodology is actually to take a weighted average of the likelihood, actually, rather than just a single point. And this will turn out to be, at least in the case that we're considering, will turn out to be equivalent to the MLE when you look at the expectation of that weighted likelihood. And so that would be a point estimator, but because it's a weighted average, then actually this will give us a lot more than just a point estimator. So it will be more powerful than the MLE, at least to some degree. But we will show essentially through what is called the Bernstein-von Mises theorem that pretty much, the MLE and the Bayesian methodology are going to be doing equivalent things. Yeah. So I don't know whether I can sort of motivate it better than that, but we should probably get started. Okay, so again, do raise any questions that you think were unclear or not. So let's get started then with the second, the second block. So we've been talking about the principle, the likelihood principle, and then we can now talk about what we're going to call. So let me just write here a 2. Yep. 2. And this would be precisely the asymptotic theory. Asymptotic theory for the MLE, yeah, or for MLEs, if you like, maximum likelihood estimators. Okay. So maybe let's have again, some sort of more intuitive understanding as to what we're going to try to get to by the end of the section, which, by the way, is going to take a few lectures. So today will be a bit more about sort of the stochastic convergence concepts that we're going to be using. So then let's maybe remind you from the last lecture that not all estimators are unbiased, right? But what is true is that, pretty much every reasonable estimator is what is called, we can refer to as asymptotically unbiased. Okay, so you can probably guess what this is, because I think I may have actually talked about it already. So what does that mean? Well, it just means that if we take the expectation, under some distribution with parameter theta of our estimator of theta, then this will converge to theta, as we get more and more data. Okay, so rather than having an equality for every n, we have it in the limit as we get more and more data. Okay, and this has to happen for all theta in the parameter space. Okay, so then this is obviously something that we want to have, but this doesn't really. It's not necessarily going to talk. It's not explicitly, or it doesn't really imply, some sort of actual convergence, strong convergence of this sort of estimator to theta. So let's talk about a few concepts. So then, sorry, that's a bit bad. Okay, better. I think. Yeah, I hope that's fine. Okay, so so closely related concept, closely related, and actually stronger concept is consistency. Okay, so what does this say? Well, it is saying that this guy is indeed going to converge to theta as n goes to infinity, and this has to happen, of course, under. I mean, we have no expectation here where we can fix this p theta, which we did above with the subscript in the expectation, but here. We have to explicitly say that this is whenever the true parameter, or whenever the data is coming from p theta for this theta, and again, this is for all theta in the parameter space. And then you'll be now saying, well, good, okay, so the limit is theta, that's a fixed quantity, fine. But what about the left-hand side, right? Our estimator here is a random quantity, right? So it's not like you can just say, well, that converges to theta. You need to specify in what sense that is, right? Because once you have randomness, you really have a lot of ways of convergence. Yeah? So we'll talk about this in a second, in what sense this is. But before that, just assume that this is some stochastic convergence sense. And before that, let me just carry on with the motivation. So fact is that usually, because we can now wonder, right? Okay, so this converges to that, but how fast does it do it, right? So let me say something about that. So, so the rate of convergence is no faster than square root of n. Yeah. So let's maybe clarify what this means, i.e., if we multiply the difference of the two quantities by n to the alpha, this guy is not bounded whenever alpha is larger than 1/2. And this not bounded, I'm sort of putting like quotation marks, not because this really defines any concept, but rather because it's not a very precise statement. Just in the same way that we put the question mark above, because the convergence had to be specified, this stochastic convergence here, the boundedness, again, if this is something random, it may very well take, extremely large or even just, arbitrarily large values. But does that really make it unbounded? Well, yes, in the very strict sense, but actually it may be that as long as you are, generally speaking, within some compact set, then that could be some sort of boundedness. Yeah? And this is indeed what we'll see. And so, so I guess, okay, so having said this, a reasonable, I guess, optimality, let's see, so thus, a reasonable optimality criterion is the following. So it's that we can take the variance of the left-hand side and the theta, sorry, not alpha, but rather square root, and have, so this of course is going to be simply n times the variance and the theta of the estimator. And so, what we can hope at best to get is, that, sorry, that's not it. So it should be I minus 1. So this is the Fisher information matrix, but sort of inverse, yeah? And this is for all theta in the parameter space. So why is this? Well, what I'm saying here is that, this already implies that the rate of convergence is going to be this best rate of convergence, which is the square root of n, and and then what we are doing here is actually even specifying or even achieving the best constant. So it's not only the speed, but also the constant in front of the rate. Yeah? And this constant, of course, must be lower bounded by this, it must be lower bounded through the Cramer-Rao lower bound, yeah, which is something that sort of is embedded here, yeah, in this optimality. Okay, so so these are things that we're going to be wishing for, okay, and this in particular is called asymptotic efficiency. Asymptotic efficiency. So I must have hopefully written, or at the very least spoken about efficiency as being, the property of an estimator that achieves the Cramer-Rao lower bound for finite samples. And so if you want to talk about it asymptotically, then that you may not achieve the bound for finite samples, but only in the limit, then you talk about asymptotic efficiency. Okay. And so now the claim that we're going to eventually show in this section is the following. So claim is that under very general assumptions, MLEs are asymptotically efficient. Asymptotically efficient. And in fact, we're going to say much more than that. So in fact, under let's see, maybe let's write it this way. So MLE. So the MLE is going to be approximately and normally distributed with mean theta and variance 1 over n I to, or the inverse Fisher. Yeah? So this is all under p theta and for all theta in the parameter space. So just the usual thing. Yeah? And this is maybe not a dot, and this is and this approximation is in a distributional sense. Let me say out so the distribution. Okay, so I claim that this is, as I said, that this is quite general and stronger. Yeah, so this is, let me just say, this is quite strong. Strong. Indeed. It doesn't only imply this asymptotic efficiency, but it will allow us to make derive inferential procedures. Yeah? It will allow us to derive or construct inferential procedures. So remember, I'm talking about the three that I spoke about in the first lecture. Okay, so let me expand on this, or maybe comment on this. So let's look at these approximation that we had there. So what is this saying? Well, forget about the normality, yeah, for the moment. What we have is that, we have a distribution that is centered around theta. Good, right? Because we said that we're going to show asymptotic efficiency, and asymptotic efficiency will mean necessarily consistency. So yes, of course, it has to go to theta in some sense, right? In some way. And then, the variance is exactly what we are hoping for in terms of optimality. So good. So we've got those two things. So far, we've only really said that the MLE is asymptotically efficient. But now we have even the distribution of its fluctuations, right? So the MLE is a random quantity, and so if we look at the fluctuations, then this is saying that actually it's going to be normally distributed with this mean and variance, yeah? And so, of course, having access to the distribution, in this case, limiting distribution, so we may not be able, and generally we're not able to talk about the exact distribution for finite samples. But asymptotically, what we get is that we can derive, if we understand the fluctuations, then it means that, we can say where the theta is. Well, we can, I guess, infer more or less where it is, but also we can create tests and we can create confidence intervals because we know precisely the displacement, the randomness of this guy. Yeah. Okay, so this is why we'll be able to construct inferential procedures. So this is just the ideas that you must have seen in Stats 1B, for instance, with the usual Gaussian linear model, yeah? In which actually you have an MLE, but you even know the distribution for finite samples. Yeah? Anyway, but this is just the usual game of deriving inferential procedures from distributional properties. Yeah. Okay, so let's see how I'm doing with time. So not great, actually. Okay. Yeah. Okay. Yeah. So I'm going to go a bit faster here, just because what I'm going to talk about, I think you must have seen it in probability, or certainly you will have seen it in probability and measure. Of course, not everyone may be attending that, but so let me just go through these concepts. So we need stochastic convergence concepts. That concepts that we're going to need, of course, to show all of the above, right? Okay, so let's get a first definition going. So let's take a sequence of random variables and another random variable. These are going to be random variables in, say, RD, okay? And we need some probability space, and this probability space, okay? And I will say something about this probability space later on in the case of IID sequence, yeah? because actually it is very important. But I guess for the time being, you should just think that the probability space is fixed. That's super important, and all of the random variables can be realized in that space. Okay, I will go back to that. Okay, so okay, so far we can now define two concepts. So we say that xn converges to x almost surely or equivalently written, we say that this converges to that almost surely as n goes to infinity. We may sometimes drop the n going to infinity. Yeah, converges almost surely if we have the following. So if the probability of the set of events such that the difference between the two, and this is of course at the omega, so the set in which these guys are going to go to 0 as n goes to infinity, we wish it to be, which by the way we can write it, we'll sometimes, well, generally speaking, we will drop the omegas, so we want this to have probability 1. What does that mean? Well, it means that if we think of the x's simply as mappings from this event space to the RD, then we wish to have precisely the set in which you're not going to get convergence pointwise is is a null set. Okay, if you're used to the terminology of probability and measure. So it's basically a null set is a set that has probability 0. Yeah. Okay. So now let's talk about xn converging to x in probability. Okay. Or also written as xnp. N goes to infinity. Again, we may drop that. So if we have the following, so we say that, let me maybe now just write this shortened version. So the probability that this is larger than epsilon goes to 0 as n goes to infinity for all epsilon larger than 0. Okay, so of course this is weaker than almost sure convergence. Yeah? So this is not really talking about pointwise convergence. Yeah? Okay, so and of course, well, we'll go into this in a second. Okay, so let me make a remark about these two, because we've been talking, so these guys, these random variables are vectors, right, with coordinates. So if we look at the jth coordinate and this converges in almost surely or in probability to, and note that I'm now dropping just the ends, I guess for laziness. So this turns out to be equivalent to, the notions that we had already. So what this is saying is that, for almost sure convergence and probability, it is equivalent to look at the coordinates. Yeah? So for almost sure convergence, this should be sort of very clear, immediate. For almost sure convergence, and example sheet for convergence in probability. Yeah. Okay. So let's now introduce a third stochastic convergence concept, which is, sorry, that's not what I mean. I just want to say definition 2. Definition 2, we have that xn converges to x in distribution which can also be written, very creatively. Now we have a d instead. So this, if the following holds, and is that you wish the probability of this guy being less or equal than some t to go as n goes to infinity to the probability of this guy being less or equal than t, but not for every t. So you want it to be for every, for every t, such that the mapping that goes from t to this guy is continuous. Yeah? So you want for all the continuity points of this distribution function. Okay. And by the way, just to as notation, so when we have a vector, of course, this means just simply looking at the coordinates. Yeah. This is D, I believe. Okay, so we've got this. Let's now talk about, so let's now give some, statements about these things. I may be going a bit over the time. Okay, so, so proposition 1. So we're going to have several concepts, which is, convergence almost surely implies convergence in probability, which implies convergence in distribution. Okay. Then the second one is what is called the continuous mapping theorem. Very, very useful theorem, which says the following. So if we have our sequence and x, be random variables in some calligraphic x. So this is a sample space that is contained again now in Rd, but it can be that it's a strict subset. And what's going on here? And G, and let us introduce now a function that goes from this sample space to R, and this function has to be continuous, okay, on that calligraphic X. And then what we get, if, or maybe let's say if, let's start with if. So if, xn converges to x almost surely, or in probability, or in distribution, then we have that the images are also going to converge in the respective senses. Yeah. So this is all respectively. Yeah, that's important. Okay. Okay, and then now another very powerful result, which is actually the result of the continuous mapping theorem, so it can be proved using the continuous mapping theorem, is what is called Slutsky's lemma, but just because it is used, so regularly that it's just been given a name, basically. Okay, so we have Slutsky's lemma, which is saying the following. Yeah? So assume that xn converges in distribution to some x, and then we have another sequence that is yn, and this converges to C in distribution, where C is non-stochastic. Okay, so then what we get is following statements. So we get A. So then, first of all, we get that this yn, whenever you convert to a constant in distribution, you also convert to it in probability. Then we can also look at the sum of these guys, and this is going to go to x plus c, as you would imagine, and this is in distribution. C, we have the, so we can look just simply at the products now. So let's focus first on the d equal 1 case. So we have xn times yn is going to convert in distribution to c times x. Yeah? And if we divide the xn, then this is going to go to the division if, of course, and this is necessary, if the constant is distinct from 0. Yeah. And then what about the multidimensional version? So assume that an is a random matrix such that it converges, just in the same way that we had convergence in distribution before. Sorry, in probable. Well, yes, we started with distribution, but that implies probability, so we can directly now write this as probability, and this is of course because random matrix is just a matrix of random variables, and convergence of it is simply convergence of its coordinates, by the same sort of argument that we had, or that you'll use in these in the example sheet for the vectors. So then, if this is non-stochastic, of course, we get that we can now talk about the product, going to the product. Yeah. Okay, so last bit here is as follows. So now I'm going back to this concept of boundedness. So if xn converges in distribution to x, then we know that this doesn't imply convergence in probability, but does it imply something in probability? And the answer is yes. So then what we get is that the sequence is bounded in probability. Okay, what do I mean by that? Well, that's simple here. Well, this can also be written, by the way, as OP1. Okay, so it's just the usual big O that you would have in sequences in analysis, but now we need to, of course, specify something about the randomness, and so the meaning of this is that for all epsilon greater than 0, there exists a constant large enough that depends on epsilon, such that the probability of this guy, and this has to be in, of course, norm of this guy xn. Yes. So this being larger than m epsilon would be less than epsilon. So for all epsilon, we can find, and this is what I was saying before. So in some sense, we have a compact set that will accumulate most of the mass, as much mass as we like. Yeah? And let me just point out that this is one direction, the so-called direction of Prokhorov's theorem. So the converse basically what it says is that if xn is an OP1, so if it is a bounded in probability random variable or sequence, excuse me, then we do sort of recover this convergence in distribution, but under subsequences. Yeah. So via subsequences. Okay. So let's now say something about what we talk about next in next lecture are the law of large numbers and the central limit theorem. So before I introduce that, let me just finish the lecture by clarifying what I said I would do when we introduced the stochastic convergence concepts, in which what we had was, I remind you that we started with this definition one in which we had this sequence and the random variable to be random variables that are defined on a fixed probability space, and so they can be realized there. Okay, so then the case that we are always interested in this course is this IID case, and so we'll be thinking, what is this? What is that probability space? How can we have a probability space where we can have an infinite sequence of random variables to be defined? So let's consider, as I'm just saying now, consider rather than a general sequence, so consider now an infinite sequence x1, x2, so on, of IID copies of x. Okay, and so the question I was trying to sort of emphasize here is on what fixed probability space can we make statements, and in this case it's very important that they are simultaneous statements about the stochastic behavior of these guys, yeah, of x1 to x2 and so on. So let me briefly answer that. Such sequence can be, and I will clarify this in a second, can be realized as, I guess this is a technicality that really belongs more to probability and measure, so you will not be examined on this, but I think it's good that you know it, that what we're talking about here. So it can be realized as the coordinate projection of the infinite, so-called, of the infinite probability, excuse me, infinite product probability space given by the following. This is an omega a P that actually is the Euclidean Cartesian product of the R's, and then the product sigma algebra, and the so-called infinite product probability measure, and which is sometimes denoted by PR, and this is, as I'm saying, is this guy, and this is just this product, these P's. So this really belongs to problem mesh. And so let me say a few words about this. You'll be thinking, what on earth is this guy bringing up? So whenever you want to make, think of the finite dimensional case, as in when we have finitely many random variables. If you have finitely many random variables and you want to say something about them simultaneously at the same time, then what do you need? You need the joint distribution. Yeah? I mean, that's the absolute key. That's what describes what uniquely specifies everything about this finite collection of random variables. So now, of course, if we're talking about having infinitely many and we want to make statements that are asymptotic, we need to know, we need to work with this joint distribution. And in this case, it's an infinite sort of joint distribution, if you like. And so you'd think, well, yeah, okay, I mean, that clearly that distribution, will be somehow, related to this Cartesian product. And yeah, okay, maybe the Borel sigma algebra is not too bad. But then when you multiply probability measures by themselves, and you do this infinitely many times, countably infinitely many times, these are guys that are between 0 and 1. Why would the infinite product be well defined? Yeah. So you need to justify how this is defined. Yeah. And so that belongs to probability and measure. But I guess all I want to say is that, all I want to emphasize is that, we need to construct some sort of space that doesn't change, basically, because what we said in the 3 convergence concepts was that, and I remind you, when we were here, I was speaking of a single, this definition too, of a single P here, and a single P here, right? So if we don't introduce this infinite product probability measure, then what will happen is that you can, what you need is to be talking about, all of the random variables up until n. It wouldn't really work in almost sure convergence, but in probability, well, you could take this P to be actually P to the n, small n. But then the problem is that then the probability measure is going to be changing. Yeah? And that's not something that is within the definition of convergence in probability. Convergence in probability has to be with respect to a fixed measure. Okay, and so you will, if you go into this field to do more sort of maths and research and so on, people sort of are a bit sloppy about this. I guess, well, I don't know whether you can say sloppy, but they sort of very implicitly assume it. Yeah, they silently assume this, and may even state here that they have P to the n, small n. But just for you to be aware that that's not strictly speaking correct, and one has to talk about this infinite product measure. Okay, so we're done. I hope you enjoyed, and I'll see you again next week.